Hi everyone. For section 1.2, we're going to talk about angle bisectors. We already know what an angle bisector is, but we're going to learn a theorem about them, and then we're going to learn one more new vocab word. But let's start with a quick review. An angle bisector, we know what an angle is, we know what a bisector is. So basically an angle bisector is something that cuts an angle exactly in half. It can be a line segment, or a ray, anything like that. So here's a picture of an angle bisector. That red line segment in the middle, OP, bisects angle AOB, which is the black angle, the big one. And the reason we know that it bisects is because these two angles here are marked congruent. And that's what a bisector does. It cuts something into two congruent pieces. We saw segment bisectors, now we've seen angle bisectors. So here's the angle bisector theorem. It's kind of similar to what we did yesterday with the perpendicular bisector theorem. It says if you pick any point on an angle bisector and then connect it to both sides of the angle with perpendicular lines, then those line segments are congruent. Now that might sound a little confusing. Here's a picture. So what we have, it's very similar to the picture we just saw, different letters though. So this time we have ray BD, that's the one going down the middle there, and that's bisecting angle ABC. So I chose a point on the bisector, D, and actually, you know what I should have done in this picture? Just so we know it's an angle bisector, I should have marked these angles congruent. So let's do that. So now that we know it's an angle bisector, I picked that point D on it, I connected it to the two sides of the angle using perpendicular lines. That's those red lines right there. Now what our theorem says is when you do that, those two line segments will always be congruent. So line segment AD is congruent to line segment DC. So let's do an example. I'm going to use the same picture, and I'm going to say for this problem that line segment AD here is 5x plus 7, and line segment CD is 22. So the first step, we talked about this in yesterday's notes, the first step to this type of question is to realize the relationship, and we just said the relationship. The relationship is that these two line segments are congruent, or basically these two expressions here are equal. If I give you the length of two congruent line segments, then those things are equal. So that's how I'm going to solve the problem. I'm going to take those two things, 5x plus 7 and 22, I'm going to set them equal, and I'm going to solve for x. So I'll start by subtracting 7 from both sides. Cancel out that 7. Leaves just 5x here. 22 minus 7 is 15. And then we'll finish up by dividing by 5. Those cancel. 15 divided by 5 is 3. And that's our answer. X equals 3. So nice, easy question. The one thing I'm going to remind you of, I said the same thing in our last day of notes. Even though it is what worked for this question, when you see a question like this, don't just automatically set things equal to each other. Don't just look at the picture and go, 5x plus 7, 22, that's my equation. 5x plus 7 equals 22. It did work for this one, but it doesn't work all the time. So remember, the first step of every question like this, think about your theorems, find the relationship between what's been given in the picture. Okay, so here's our new vocab word for today. It's called an incenter. And one thing that can be a little tricky here, you might get this confused with circumcenter, which we learned yesterday. So an incenter is the point in a triangle where all three angle bisectors meet. So, and again, I'll mark up this picture. I should have done it originally, but the way we would know that these are all angle bisectors, I could have marked this angle congruent to this angle, 1. This one congruent to this one with 2. And this one congruent to this one with 3. Now we know that those 3 lines coming from each vertex are an angle bisector, and that's what makes point H the incenter. Now, what our theorem says is that in this picture, each of these three are congruent. HF, HE, and HD are all congruent in that picture. That's the theorem. That's the incenter theorem. Now, here's what I was saying can be kind of tricky. The theorem we learned yesterday was exactly the opposite. You draw the perpendicular bisectors, and then the distance to the vertices, is the same. This one says you draw the angle bisectors, and the distance to the sides is the same. So don't get them confused. One of them, yesterday's, was called a circumcenter. That's when you use perpendicular bisectors. Today's is called the incenter, when you use angle bisectors. But basically, wherever those three things meet gives you an important point, and that point is equidistant to something. If when you do the angle bisectors, when the lines come from the angle, it's equidistant to the sides. That's today's theorem. And when you do perpendicular bisectors coming from the sides, the distance to the angle is equal. So here is our last example for today. I'll use the same picture again. And I'm going to give you a little bit of information, so let's fill it in. So I said BD is 10, that would be right here. BH is 12, that would be this one right here. And we want to find HF, which is this question mark over here. Now, just like the example we did yesterday, there's a whole bunch of right triangles in this picture. Now the question mark, I don't know anything about those triangles. I can't do Pythagorean theorem on this triangle up here, or this triangle down here, because I don't have any numbers on it. But what I could do is I could do Pythagorean theorem on this bottom triangle right here. So let's say I want to do Pythagorean theorem on this triangle right here, and I'm going to find this question mark right here. Now, based on our theorem that we just learned, this one, and this one are all congruent. So even though I asked you guys to find this one here, if I find this one here, it's also the answer to the question. So it's not two steps like yesterday. I'm just going to do Pythagorean theorem once, and when I find that question mark, that's the answer to my question. Now, it is Pythagorean theorem, so I'm going to do a squared plus b squared equals c squared. Now the right angle in that triangle is angle D. You can tell it's got that green box to it, but remember when you have a right angle, it's the same on both sides. So this angle D down here is the right angle, which means the 12 is the hypotenuse, and that has to be C. So I'm going to put the 12 squared over here. Now the other two sides are, number one, the question mark, which is what I want to find, and then number two is a 10. Just pick A or B and put 10 and solve for the other one. It doesn't matter which one you do. So I'm going to leave A. We'll say that's the one we're going to try to find, and I'm going to put 10 for B. So what I have, and if you look closely, for a squared plus b squared equals c squared, here's my a squared, that's the question mark I'm trying to find. Here's my b squared, that's the other leg, and here's my c squared, that's the hypotenuse. So, 10 squared is 100, 10 times 10, I can do that in my head, 100. 12 squared is 144, 12 times 12. To finish solving for a, the first thing I would do is subtract 100 from each side, cancel that out. So a squared equals 44. Then we cancel out our squared with a square root. We've been doing Pythagorean theorem for like 3 or 4 days in a row now, so that should be feeling pretty comfortable with you. Once you get to the point where you've solved for either a squared, b squared, or c squared, you always use that square root to cancel. So my answer is the square root of 44. I can do that on a calculator. It's going to be, I know it's going to be pretty close to 7, because the square root of 49 is 7. It's a little bit less than that, so it's going to be 6 point something. I'll pause real quick. I'll grab a calculator so we can get in a close approximation. Yeah, I got about 6.63 for that one. So the key to that one, well, the work was Pythagorean theorem, but the key to that one was realizing, using our theorem, to realize that even though I asked you guys to find this question mark over here, it was the same as this one right here. Those are congruent by our theorem from today. Those are because that point is the in-center. It's equidistant from the sides.